Do you see my screen? Full screen, hopefully. Do you see the full screen?
I do. I think it's good.
Okay, perfect. Thank you very much, Brian. I'm Isabelle Ruin, and I'm going to present the work that I've been doing with Galatea 30. So we are from France, and the CNRS and the Institute of Geoscience of the Environment. And I'm a social geographer, and I've been studying mostly vulnerability to flash floods, and from basically observation of especially behaviors during crisis toward modeling those behaviors and integrating them to kind of impact-based forecast. So that's what I'm going to talk about today, and we're giving you some examples from 3 projects related to that. So here. Next slide. So basically, what do we want to do with impact-based forecasting? Basically, it's related to the understanding of the social and behavioral driver of impact variability. So basically, to forecast those variability related to different parameters that could be either from the hazard side or from the social vulnerability side. And the objective of this impact-based forecasting is to limit direct and also indirect impacts of the threatening event, and basically to help decision makers to make sense of the situation, the detection of the situation toward the crisis, and to basically adopt appropriate and timely actions. So on this slide, you can see that there's, of course, several components to take into account to be able to do impact-based forecasting. And of course, one is the weather hazard, and it's not what I'm going to talk most about, but mostly I'm going to concentrate on how to integrate social and physical vulnerability into those forecasts. So social and physical vulnerability are related to 3 main components. One is exposure, and exposure is basically the spatial and temporal conjunction of the hazard and the elements that are at stake. As you can see here, it's basically all the elements that you can see in the blue bubbles in the middle. The sensitivity would be related to the degree to which humans, environment, and social ecological systems may be affected by specific hazards. So, of course, if you have a basement floor a floor base at the basement, apartment at the basement, and if it gets flooded, there's the big chance that you would be affected. But if you have 2-story houses, then you can go upstairs and there would be, you still affect, but it could be less, let's say, dramatic. So that's an example. But the second thing, third component is the coping capacity, and it's really related to how the system or elements of the system can adapt and accommodate to basically avoid adverse effects. So it's related to how people can behave to avoid the effects, but not only people, but also the organizations of the society, like warnings and things like that, would be under this category somehow. So just to show you that basically, if I go back, to this previous slide, I mean, this slide looks like a little bit of static things, but actually what's the problem is that everything moves in space and time. I mean, the hazard would be evolving and increasing or decreasing of the flood, and at the same time, the society is also driven by rhythm, like social rhythms. So you're not all the time in your schools or in your home. You move, and some elements are more important during some times of the day, while other would be more important during the night. So this is very much to take into account. And as you can see in this second slide, if we looked when we look at flood fatalities in US, so in like 15, more than 15 years of data set, and we looked at more than 1,000 fatalities for about 700 events. And you can see that depending on the circumstances of the fatalities, there is a very different temporal patterns of the fatalities or the accidents that conduct to fatalities. And we can see here there's 6 different circumstances. The first one, which drives the most of the fatalities, are nature related. And the second one would be the campground and recreation outside, like close to stream or in the open air. You have also a permanent building, a mobile home, and other things. And as you can see here, and the colors relate to the number of victims. Red is a higher number. You can see that in some circumstances, some circumstances are completely different, show completely different patterns than others. If you look at the vehicle related, of course, you would see that the timing is more related to the timing of the going to work or coming back from work, and also the evening life related to activity like shopping or outside social things. If you look at campsite and things like that, it would be more related to activities that you might have either during the night because you're sleeping in a tent and you're not protected at all, or during the day where you're doing activities like in canyons or things like that. For the outside, finally, most of the fatalities happen during daylight hours, when people are doing errands and leisurely activities in the outside. Permanent buildings are more related to the evening when actually there's a rise of the water, and when people start to get a bit worried during darker conditions. So basically, you can see that there's very different patterns depending on the situation. So those situations and the activity of people are very much to take into account if you want to predict somehow your impacts on people. For instance, one way of predicting is also to look at what is the routine, the usual activity-based travel patterns. And these types of data can be extracted from census data. And as you can see here, it's a representation of the different types of or proportion of people doing different types of activity during different hours of the day. And you can see, of course, that a lot of these activities are also related to travel patterns, routine travel patterns that figure here in a pink, red pink. And of course, if you don't take that into account and these 2 bumps here, then you don't really you can't really draw a picture of where people are and what they are doing and how they can be affected in those different circumstances. So it is important to take that into account. So from these first observations and from data and things like that, we also, and of course from the theories, many people social scientists have worked on this domain, and what we propose here is a theoretical scheme to show how to integrate somehow those different aspects of exposure, sensitivity, and coping capacity, and looking at both fast evolving processes and slow evolving processes, and how those would make would trigger different types of impacts, either high or lower impacts. So related to that, of course, you have some risk governance parameters, land use, which are more static. Also individual status, which would be related to their physical conditions, social capital, socioeconomic dependencies, but also more cognitive aspects that would be related to risk perception or cognitive mapping and related to coping capacity. All these, of course, is kind of longer term kind of processes, but you can look also at shorter term processes related to how people, based on these background, let's say, would have different perception of the situation and how they consider the crisis circumstances and how they can react or cope with those specific circumstances based on the coupled place activity where they are at and what they are doing at that time. All these will condition how they make sense of the situation and how they decide what to do in that case. So based on this scheme, we basically propose a different modeling approach, and I will now detail two of them, basically coming from different projects. One is related to a project that we had with the National Severe Storm Laboratory in US, and which concerned actually the old US to do some human impact forecasting for flash floods at the resolution of the census tract. And the other is related to a French project called MobiClimax, and which is related to the mobility modeling, the mob risk dynamic model, and the resolution is much higher, kilometer, but it concerns a smaller part of the smaller geographical extent, for instance. So I'll go to the first model, and of course for this model, I mean, it's the statistical model, and we started from learning from fatality data, which are very important data sets that comes from the NCDC storm database. And based on those data, basically looking at what was the characteristics of the people who died from flooding in the past 20 or so years, we looked at those differences in terms of gender and also ages related to those different circumstances that I talked about earlier. As you can see, of course, the most dangerous circumstances is related to vehicle related, then followed by outside close to stream circumstances, and then a campground or recreational area, and then permanent building and mobile home. As you can see, those circumstances are somehow different if you look at the number of flash flood by fatal events, as the campground circumstances would make more people would die a bigger number for each event. Anyway, what we figured out from that is that, of course, these different circumstances are also linked with different socio-demographic characteristics of the people. For instance, nature-related would be more middle-aged people, as well as campground and recreation area. Outside is more related to younger people, and elderly are for permanent building, and the middle age is more related to mobile home. There's also a big difference in between the genders for the faster reactions of the catchment, so more flash flooding situation for vehicle-related outside and campground. It's more related to male. I mean, male are more often in trouble than women. And the other circumstances are more related to elderly, middle age, and somehow it's more mixed between male and women. How did we do from there? Basically, we and Galatia did this work, Galatia 30. She basically built a big database with all the entry of the different events. And she built another database related, which would be adding different proxy variable that represent the different vulnerability and exposure factors. Based on that, machine learning modeling was used to classify the accident that gave fatalities and the one that gave no fatalities, and to basically figure out which were the important drivers of these differentiation between the two. Based on that, she was able to build this model, and this model was done for the whole US and at the scale of the county. And as you can see here, for the state of Texas on the case study, Texas and Oklahoma, We also compare the results of these probability of human risk related to vehicle accidents to the red points to the observation related to fatalities and also social media. And as we can see, it works. It's of course not perfect, but it works quite well, and it's a very encouraging result to go this direction with random forest modeling. As we have seen from this modeling, the unit stream flow and precipitation duration, and also the number of commuters arriving by vehicle in the workplace were very dominant factors triggering the results. Now I would like to go to another example, the one in France, for the mob risk, which took a different way of modeling because we didn't have access to that very detailed impact data. So we had to figure out another way to do it, which is called the Discrete event emulator, which is quite close to something that is called Agentbased modeling. And to do that, we of course have a database, and this simulator helps to put together the dynamic of the environment from modeling of the hazard, the dynamic of the individual and their mobility, and copying behavior. So we have several models that put together all this in action to see interactions between those and the result in terms of probability of accidents. Of course, you need to define a space-time window and to run the model for a specific event. So we did for past event to start with. So basically, it uses data about road submersion and the probability of road submersion of this road from hazard modeling, and also road user exposure, which use activity-based mobility model and decision-making models that I will also show you soon. So the first is an activity-based approach, which is the mobility is a result of the need to conduct activity, which are distributed in space and time, and all this can be done from census data that propose a daily schedule that you can attribute to people based on their socioeconomic characteristics. Then you can locate this activity in space related to also census data. So you know where residential places are or where working places are, and all the road networks. And then you have to look for, of course, how people choose their route, and we use the shorter path algorithm here. Then we use another model called, it's a Bayesian model to take into account copying behavior. And the idea with that is to basically look at how people would behave based on different observable variables like environmental sign, trip purposes, as we consider that the flexibility of trips are very depending on the type of the mobility, the purpose of your trips. And all these would come to an evaluation of danger and an evaluation of the trip flexibility that will influence the decisions to adapt or not your trips and your to cancel your trip, to go back home, to replanify or your activities. And this is all ways to also test hypotheses of what would it change, for instance, if you would give another type of alarm, you change the lead time, or you change different, the timing of the event would be like, instead of being in the night, it would be in the day or things like that. So you can all play with that. The result is also something that we can look at in terms of the differences of exposure of the people, which is the point line, and the black line, which are the people that are potentially in danger, by crossing this, basically the probability of flooding of the roads where people go. So basically you look at the itinerary of people, daily itinerary based on their mobility, daily mobility, and how these daily mobilities and itinerary are basically impacted by the current flooding. And then you add this component of decision making when they are in front of flooding or where they start a new activity. And all these give you some kind of quantitative evaluation of the number of people that would be in danger in such circumstances. Now I would like to end this presentation with a new technique of modeling that we now currently developed. It's related to agent-based modeling, and this time it's even more small scale, as it really target the decision of agents and how agents, which are the people in crisis, and how those different decisions may, so how agents between each other would interact and would come up with a potentially collective decision or emergent situation, but also how agents would interact with the evolving environment. So this is an idea of how we can put all the observation of behaviors and understanding that we had so far, based on very different types of studies, empirical and theoretical knowledge that we gained from past experience, to basically model and code all these different behaviors into agent-based modeling, where you can also couple the dynamic of the environment, the warning, the evacuation, some alerts and things like that, to see how all this would interact to come up with different types of impacts. So that was very fast. I'm sorry. I'm going to go to conclusion now, and hopefully if you have any questions. So for all these kind of modelings, which include vulnerability, exposure, and of course, which also integrate asset modelings, models anyway needs to be adapted to the users. So what type of impact do you want to model? And you really need to have the user on board since the beginning of your development. And it is also very good to have a user group that you can interact with. It's also very important to learn about critical weather patterns, thresholds from those who are impacted. So looking at using different types of data collection, either it could be interviews to have very rich information, or more like questionnaire survey, using high resolution things, and also, if possible, having a view of all this on the longer time period. Also, the last point is that modeling even in social science needs observation and data for calibration, validation. So we really need to merge traditional social science methods with new participatory methods like social media, crowdsourced data sets, fierce games. All these would be very interesting tools, even though for now, I mean, the methodology to use them in a robust way is still under progress. So hopefully, I hope this was not too fast, and I would like to take a question if you have any. Thank you very much.
Thanks, Isabelle. That was really great. A lot of content in a short period of time.
Too much.
Thanks so much. No, it's fine. I think you've got a couple of really good questions. I'm going to try and tie the two together because we're just, we're running. This is an experiment in MS Teams as we go through this. So from René Sieber and Armel Castellan, two questions about how basically how we transfer this type of approach or knowledge. One from René more, is it really transferable to other places, and what would be needed done to make it transferable? And the second one is more related to how you can use this in an operational forecasting or warning center context. So how do you successfully bring this into an operational environment and have the desk forecaster, I guess, change their approach in real time or near real time to take advantage of this, input of information? Yeah.
Okay, so for the first, the transferability, this is very much related to the data set you have, and also the objective. I mean, the scale at which you want to work. If it's for the whole country, as the example of US that I showed, or if it's more localized, this is completely different. For instance, we couldn't use the same approach that we used for US in France because we didn't have any access to to precise impact data. So it is very much related to these data sets. So this is the first thing to look at, is what data are available, can you learn from them? And if not, then you would need to go more on to more, let's say, scenario-based type of modeling, where you kind of put together the knowledge you gain from theoretical research, empirical research so far, but with not real data beyond that. So, so this is how you would choose between the two. And then if I go to the second question, of course, also related to that, definitely the agent-based modeling or the discrete event simulator that I showed are quite difficult to integrate in an impact forecasting chain, because it takes some time to run this modeling. So, and it can't really be done in real time for now, because it's too much. It's too difficult, and the numerical prediction needs to do that quite fast. So, nevertheless, those models that could be run in preparation, in before crisis or between crises, somehow to learn how to derive synthetic indicators from what you learn from those models. You could derive synthetic indicators from data sets that are existing. And then from there, you can use those synthetic indicators much more easily, I think, in the real-time forecasting process, I think.
Okay, thanks, Isabelle. I think that's all the time we have for questions right now. I notice Marianne and perhaps others have listed questions. Keep the questions coming as you go through. We'll return to some at the end, and we'll also try and provide the questions to the researchers who are presenting as well, and they can develop more responses to specific inquiries later on, or follow up yourself later. So thanks again, Isabelle, for a great talk and for the questions.
Thank you.
Sarah, you're next. I think everyone can see the agenda, hopefully, on the screen. I'm going to give up the screen again, and Sarah's going to be talking to us about developing an integrated impact, vulnerability, and exposure knowledge base for New Zealand.
Thanks, Brian.